Okay, so we're going to finish up 2.7 here, and we left off with an exercise which gave us two functions, 1 over x squared and the square root of 9 minus x. And our task was to first compute f composed with g. So let's do that. Well, f composed with g, that's f of g of x, so that's 1 over g of x squared, which is 1 over the square root of 9 minus x quantity squared, which is 1 over 9 minus x. So that's what we get when we compute the expression. What we then want to do is find the domain of f composed with g. And remember that this was all x, where x was in the domain of g, and g of x was in the domain of f. And so here I'm going to tell you kind of the optimal method to do this. One, first, of course, is to compute the domain of g. So step 1 is find the domain of g. Step 2 is to find the domain of the expression of f composed with g. So what I mean by the expression, this expression is this guy. So the 1 over 9 minus x. And what we do then is between step 1 and step 2, we take the intersection. So we take the intersection, or what's in common between step 1 and step 2. Okay, so let's do that in order. And that step 2, really what it does actually is take care of this second condition. Okay, so this second condition for the domain of g, that's really what's happening in step 2. So let's look at g of x, step 1 here. That's the square root of 9 minus x. Whatever is inside the square root better be at least 0. So this results in x being less than or equal to 9. So the domain here is everything below 9 and including it. So this is step 1. Step 2 says, let's take the expression which we got from f composed with g. What was the expression? It was 1 over 9 minus x. So this is the expression that we got, expression for f composed with g. Now, what are the restrictions here? So the restriction for domain here well, 9 minus x can't be 0. You can't divide by 0. So x can't be 9. So what we need to combine these two. Well, x can't be 9, and we have to be in this set. So if the intersection is the condition that we must be x is in the set negative infinity to 9, and x can't be equal to 9. Well, if you take both those together, that's the domain of f composed with g, which is negative infinity. And now we just, instead of the closed bracket here, this was our closed bracket, we open the bracket there so that we remove 9. And that turns out to be the domain of f composed with g. Okay? So I guess one thing that I'm going to explain, if you're satisfied with just doing this as is, that's great. I just want to talk a little bit about how this condition 2 is taken care of when you find the domain of this expression. Well, notice, so condition 2 here, and let me do this in a different color. Remember, f of x was 1 over x squared, and g of x was the square root of 9 minus x. The domain of f, well, it was wherever it was all x where x squared is not 0. The denominator can't be 0. Well, when is the denominator 0? If x is 0, then the denominator is equal to 0, which we don't want. So hence, the domain of f is everything except 0. It's all x except 0. All x where x is not 0. So essentially what we want, or what we don't want, is we don't want for the composition, we don't want g of x to be 0. We don't want g of x to be 0, because f of g of x is 1 over g of x squared. And since g of x would be in the denominator there, we don't want g of x to be 0, because that would make your function being divided by 0. So, well, what does that mean? That means 9 minus x should not be 0. That means if you square both sides here, 9 minus x itself shouldn't be 0, which means x can't be 9. And that's exactly the condition that we got from our step 2, which is x can't be 9. So this is just another way of thinking about it. I wanted to show you. But if you want to think of it just as a simple two-step process, these two steps, find the domain of g and take the expression you got from the composition, which in this case was 1 over 9 minus x, find the restrictions from that, and combine the two to get your final domain here. Okay, so that's how you do these. Just to do one last, because these can get a little bit involved, let's go the other way. Let's take g composed with f. So we have that g of x is square root of 9 minus x. Let's compute g composed with f, and then find the domain of g composed with f. Well, how do you do this? Here now, for the domain, before we do the computation, let me just explain what's happening here. Here, x first gets plugged into f, and then f gets plugged into g. So here, the domain, it's all x, where x is, first of all, definitely has to be in the domain of f, right? For the first round, it definitely has to be in the domain of f. And then from here to here, f has to be in the domain of g. F of x, let me write that with, f of x has to be in the domain of g. So this is the general concept. It's just reordered. It's the same thing, but I wanted to rewrite it. So let's do part 1 now. G composed with f, g of f of x, that's part 1. That's the square root of 9 minus f of x, which is the square root of 9 minus 1 over x squared. So that's g of f of x. And now let's compute the domain of the composition. Again, it's two-step process. So step 1 in this case corresponds to finding the domain of f. So we need to find the domain of f. Well, f of x, remember, was just 1 over x squared. So it's all x except 0. X where x is not 0, right? We saw that a little bit earlier. Again, here, I'll just write off to the side. F of x was 1 over x squared. The denominator is 0 exactly when x is 0. So it's all x except 0. This is our domain. In interval notation, this is negative infinity to 0, union 0 to positive infinity, with open brackets everywhere so that you don't include 0. Okay, that's step 1. Step 2 says take the expression you got from part 1. What is that expression? It's the square root of 9 minus 1 over x squared. We say, okay, we want to find the domain of this expression. So what x values are allowed? That's the question. Well, we know that whenever you have a square root, 9 minus 1 over x squared has to be greater than or equal to 0. Also, because x here is in the denominator, x itself can't be 0, which actually we saw from part 1, but it's useful, I guess, to see it again. But the key new thing is this part. 9 minus 1 over x squared has to be greater than or equal to 0, which means 9 has to be greater than or equal to 1 over x squared, which, just rewriting it in a different order, 1 over x squared has to be less than or equal to 9. Now what do we do now? We multiply both sides by x squared, and notice that x squared is always positive, so we can keep the inequality exactly the way it is. So we get 1 greater than or equal to 9x squared. Or, now dividing by 9 on both sides, you get x squared greater than or equal to 1 over 9. Okay, well, let's take the square root of both sides. Remember, when you take the square root of x squared, you get the absolute value of x. That must be greater than or equal to 1/3. Okay. Well, if you have an absolute value greater than or equal to a number, that means either x is bigger than 1/3 or x is less than or equal to negative 1/3. So recall, when you have a greater than in an absolute value, it splits into 2 different cases. So that means we get the interval negative infinity to negative 1/3, as well as the interval from 1/3 to positive infinity. So these are the values that are allowed, or that you get as the domain of the expression. So this is our domain of the expression. So what is our 2-step process? Well, step 1, the domain of f just said x can't be 0. For the domain of the expression of the composition, we got negative infinity to negative 1/3 union 1/3 to positive infinity. We need both of these to be satisfied. X can't be 0, and x has got to be in here. Well, how do we combine that? Well, it turns out that in this set, take this set right here, 0 is not in here at all. So 0 is not part of this set, right? Because 0 is between negative 1/3 and 1/3. So 0 is not even part of it. So this thing is our domain of the composition. There are no additional conditions that come from, well, there is an additional condition from the domain of f, but it's already sort of taken care of here. The 0 is not even part of it, so we don't have to worry about it. So hence the domain of the composition of G and F is equal to negative infinity to negative 1/3 union 1/3 to positive infinity. Okay, so that concludes this is the end of 2.7, and we'll catch you guys in the next video.